and so that will just so when we do finally maybe get back into Sainsbury's, maybe we can have a bit of a splurge on pizza and beer. But yeah, that'll be in the future. Okay, so we do have a code of conduct. So this covers obviously the physical events as well as online. So if you just want to check out that URL, just make sure that we follow that and make everyone safe and comfortable and not harass anyone. So yeah, if you can check that out, that'd be great. We do have Slack. I think every time I post this, we get like 2 or 3 people kind of joining the Slack group. So yeah, if you want to join there, I usually announce the meetups there as well as obviously on Twitter and various social media, and anything about the group. If you want any comments or suggestions, again, feel free to join the Slack group, and just let us all know. Fantastic. Okay. Speakers. So we are always looking for speakers. If anyone is interested or may know of anyone, simply go to this URL, or and this will be I think it's a Google form, so you can just select the month or months that you're available, and I'll get in touch with you if it's something that we'll be interested in. Again, the talks that we kind of have here, we'll try and keep them in some way related to PHP. So if you talk in JavaScript or maybe Ruby, then it might not be what we're looking for. But again, we're accepting speakers of all levels. So if you've never spoken before, don't be scared. Just fill in the form. Even if it's just an idea that you have, just fill that form in, or send a message on Twitter, or join the Slack group, and you can send me a message, and we can discuss the idea and maybe discuss the kind of talk content. I'm always happy to do that. That is pretty much it for me, I guess. Once again, I'd like to thank everyone for coming, and I'm going to actually invite Dan to talk a little bit about the platform that he's kindly provided for us. So so over to Dan.
Craig, thank you so much. Really appreciate the opportunity to come and join you quickly. As you mentioned, Craig, the platform that we're in this evening is on the Big Orange Heart website. Just really wanted to quickly mention what Big Orange Heart is, why we're here, what we're doing, why we're giving this platform out to the community. So Big Orange Heart is a registered charity supporting and promoting positive wellbeing and mental health within the remote working communities. So we're continually looking for communities to link in with, to support in different ways. We ourselves run a lot of online events, so we appreciate what it takes, the challenges that we face at this time to deliver online events. So the platform that we're in on live.bigorangeheart.org, we are donating to organisations that fit within the ethos, and obviously PHP London fits right within that framework. So Craig, really appreciate the opportunity to come on. Just want to very, very quickly mention this website, big.ht/2020. We've just opened up our annual wellbeing and mental health survey into the remote working communities. If you have the opportunity to, we'd really appreciate it. It'll take you about 3 minutes to complete. It's probably like a survey you've never come across before in terms of the structure and in terms of the way it's delivered to you. The information that we gather through that really has enabled us to literally save lives over the last 12 months from the data that we gathered on the previous survey. It really is a way to be able to give back to the community, to the remote working community in some way. So if you're able to, big.ht/2020, I'd really appreciate anyone that can complete that. So Craig, thank you. Really appreciate the opportunity to come and speak. And I will let you get back on with the PHP London event.
Thanks, Dan. Yes, as I mentioned before, I think this is the second month that we've used the platform, and yeah, it's been fantastic. Much better improvement from Zoom, and no Zoom bombing, which is always good. Okay, yeah, like I said, that's it from me. So I'd like to, just before I introduce the speaker, so we do have in the platform the ability to ask questions, so in the live chat. So if anyone has any questions at any stage throughout the talk, just put that question in there, and then we'll gather the questions for the Q&A at the end. It just means that we're not having like 15 million questions right at the end and we can't keep up. So if you can, like I said, ask any question throughout the talk, and then we can just line them up towards the end. So yeah, I think that's everything from me. So yeah, I'd like to welcome our speaker for today. So yeah, I'd like to welcome David. Yeah, so over to you, David.
Thank you very much, Craig. Cheers. All right. As Craig has said, my name is David, and I'm a senior developer advocate for a bare metal cloud company called Packet. So a little bit of information about myself. I'm from Scotland, so it's not too hot up here, unlike London and Southern England right now, which I'm grateful for. I have 9 pets. I have chinchillas, dagas, a ferret, fish, hamsters, pretty much a mini zoo. I'm a big fan of esoteric programming languages. Currently trying to do as much as I can with Rust, and I'm a big fan of Elixir, Crystal, and I'm trying to get better at Ponylang. And I'm also an active member of the Kubernetes organization and release team. You can find me on Twitter, where you're more than welcome to ask any questions after this session or over the coming days and weeks when you hopefully try to apply some of what we're going to cover today. And my username there is Rockwood. So let's just start with a little video of one of my animals. This is my ferret, wearing a jumper and a Christmas hat. So sadly, the talk only goes downhill from here. Now, today I want to talk about an introduction to time series. We're going to talk about what time series is and hopefully how it can help you write better software. But before we begin, I'm going to start with a pop quiz. Now, this works a lot better when I'm giving this talk in a physical location with people I can see raising their hands. So feel free to type your answers into the chat, and I will ask Dan or Craig to, at the end of the session, let me know which people were closest, and I will try and get you some Packet swag sometime next week. So question 1, as developers, operations people, or just people working with computers on a daily basis, we may be familiar with the concept of encoding. And what I want to throw out to you is, by a show of century, when do we feel, or when do you think that encoding was first used? I'll give you all about 10 seconds to type something into the chat. I should have been counting, but we'll just say that's roughly it. So the answer is, and I'm going to say answer loosely here in quotes, but we're going to say 410 BC, and I'm going to try and explain that. So there is some really old text called The Lives of Noble Grecians and Romans by Plutarch. Inside of that, there's a paragraph, or at least a story, about Alcibiades. And the story of Alcibiades, Alcibiades was a warrior with a ship and an army, and he would turn up to battles, not really sure of which side he was going to fight for. In fact, he was a bit of a mercenary in that regards. And it wasn't until he would show up to the battle where he would raise a flag to indicate which side he was going to side with then. So when I say encoding, yes, it's very loose. He was using a flag to transmit a message to say, hey, I am going to fight for this team. So well, hopefully someone guessed at least in the BC and not in the 80s. As far as encoding goes, not a lot changed for many, many hundreds of years. right? So it wasn't until the 14th century things progressed from like, a single flag to two flags. Right? The idea, and this two flag system was not sophisticated, right? One flag meant the enemy is coming. Two flags meant everyone come aboard the admiral's ship, right? So not exactly a sophisticated thing that had evolved over 1500 years. However, things did progress much faster after that. In the 15th century, they had a much more complex flag system, which was able to transmit a variety of different messages. And then in the 17th century, this is a system that naval fleets still use today, where you can actually transmit any message using a combination of colored flags. So one more pub quiz, one more chance at swag. Now take a lesson here from the encoding, all right? My definition of sharding is used very loosely. But when do we think sharding was first consumed? Now, your time starts now to get your answer in, and I'm going to try and talk a little bit about this. When we talk about sharding, we'd obviously, the first thing that always comes to my mind would be databases, something that's very modern. But actually, time's up, by the way. When we talk about sharding, I'm actually going to try and date this back to 150 BC. I know, crazy. And this was actually a text that was written many years later, 150 AD. And what this actually showed was that the ancient Romans, we all know that the ancient Roman legacy, right? They won all the wars, they took over the entire continent. And the way that they did that was by transmitting messages. What made the Romans so effective was they were able to transmit messages far distances. And the way that they did that was through smoke signals. Now, how does the sharding come into it? Well, they had to have a system for sending those messages. And what the ancient Romans actually did was they had tablets that were split. The letters of their alphabet were split across the tablets. And then the tablets were like an index, and the smoke signals were used to send the message saying this tablet and this letter on that, right? Now, of course, we don't have any photos from back then, but if we look at this here, we can kind of see how this worked. So they had the alphabet sharded on the tablets. On the right-hand side, they would indicate which tablet you were to look up. So in this case, there's 5 flames, which means the 5th tablet. And then on the left, they have 2 flames, which means the 2nd letter on that tablet. And they could transmit messages faster than any other army in the world, which is why they conquered everyone, just about. Okay, so whoever got closest to them, hopefully we've got some swag coming your way. If you're like me and you find weird stories like this mildly amusing, there is a book full of them. Called The Early History of Data Networks. These 2 examples were lifted from that, but the entire book is really worth a read. Really, really interesting just to see how things that we think are relatively new or modern are really, really not, and have been around for many, many centuries. All right, so what about the history of time series? Time series has to be new, and unfortunately, maybe the wrong choice of word, it's not actually that new either. And again, the Romans have done everything. So the Romans, I'm going to claim but can't prove through fact or evidence, had a concept of time series. And the reason I believe that was the ancient Romans also had commodity stock. People were able to buy or invest in companies, and they were able to sell those stocks at a profit or a loss depending on circumstances. And the most important parts about this text here is that the share prices fluctuated in value. And that is super crucial. If the price changes over time, they have to be tracking that value over time. They have to know at what price you bought and at what price you're willing to sell. So there had to be a concept of time series, even if it wasn't formally documented as the same type of time series that I may be talking about today. Now, just a couple of random facts. The first IPO ever was in the Netherlands in 1602. The US was many years later. And then in 1884, there was a paper published about the price of wheat. And why this paper is so important to time series is that this was the first ever reference I could find where time series was used as an explicit term. And what they were doing is the person that wrote the paper was trying to work out if the price of exporting goods from the UK had any sort of effect or was affected on by the import prices of cotton and silk into the UK. Now, I'm not going to suggest anyone go and read this paper. It is particularly dry and not worth your time. But still the first documented instance of time series I was able to find. Okay, so why is this important? Well, is the first time that anyone had actually ever taken the idea of applying or using the dimension of time with statistical mathematics. And that's what we're kind of going to try and introduce everyone to today, because the CTO of Influx Data actually suggests that, and Influx Data is a time series company with a time series database called Influx Db that we'll touch on later. But what he claims is that most data, I think he actually said all data, but maybe most data is best understood on the dimension of time. And if you walk away with anything today, it's hopefully that I can prove that to you of why time is so important when it comes to writing software and operating software in production. Okay, so finally, an introduction to time series. What are we going to cover? Well, I'm going to spend about 3.5 seconds telling you what time series data is. I will spend a little bit more time talking about time series databases. I am going to use InfluxDB as an example. Disclaimer, I did previously work for Influx Data. InfluxDB is the TSDB that I'm most familiar with, which is why my examples are based on it. Although I will keep everything relatively agnostic, that it can be applied to other time series databases. And then we'll talk about the value of time series data, and I'm going to get into the intricacies of that later on, but it might not be as simple as we seem, right? It's not something that we can leverage for free, unfortunately. And then we'll finish with a few stories from my SRE days and talk about how we can apply and advance the time series data to advance our concept of monitoring and observability in the modern day production and cloud native stacks. Okay, finally, what is time series data? 3.5 seconds. It is any piece of data that has a timestamp. It really is that simple. Any piece of data you have in a database that has a created data and updated data, there's a chance there's time series data there that just may not be stored as time series data. And we just want to be able to identify that and understand that. So what I have here are some events that could happen, things that I would consider to be classic time series events. And we're going to try and understand what is going on with this system. If we assume that these events all happened within a system, then we want to know how to make sense of it. So what we have first, in a kind of peachy, pinky, ready, orangey color, are things that I would consider to be bad. Right? If I've seen these events happen within my production infrastructure, I would be slightly worried. If my memory consumption is at 100%, I'm definitely concerned. If I have a health check failing, or my pods or containers or applications are being killed by the OM, I am worried. Right? These are bad events. What we have in the yellow, more orangey colors, are things that I would consider causal events. Right? These are not bad necessarily, but they have the potential to cause bad events. But deploying new software definitely can cause problems. CI started in the past could have side effects that cause problems. Pods or applications being restarted definitely have side effects and could cause problems. And probably the number one cause of issues in our production system is database migrations, right? When have they ever worked flawlessly? Very rarely. What we have in the purple, finally a color I can articulate, are things that are not particularly scary. Right? Someone committing something to Git is unlikely to be causal or be dangerous to my infrastructure, I would hope. The CPU utilization of a machine being at 12% is not something that's going to cause me great concern or lose sleep. And what we had in pink is a red herring, and it's never going to happen. Blah, blah, blah. Now, those events didn't make a lot of sense. But when we apply them on a dimension of time, we immediately understand what happened in the system. We can see that the memory hit 100% first. That caused the kernel to kill our pod. We were using Kubernetes as an example. We're using the latest tag on a container image, which automatically did a deploy that we didn't want deployed. I had a broken migration that was untested, that then ran. Our application is now in pieces, and the health checks are failing. When we have these events stored on a dimension of time, things make sense. And that's really, really important to understanding why time series is so important. And generally, when I speak to developers or operations people, the time series is not in our lexicon. It's not a word that we use, day to day, but it is a concept that we all work with day to day. What we have in front of us is time series data. And it's just logs, right? You've all seen this screen. You've all tailed this file. You're all familiar with logs. And the reason that this is time series data is that if we look at what's the first thing on any log file on the left-hand side is always a date or timestamp. And that means we have time series data because it has a time and a date. Okay, so what is time series data? We covered. What I really want to do is break it down into two different categories now. So when we talk about time series data, we have the raw form of time series data, which is irregular and events. Now, when I say raw, it means that it's unpredictable with inconsistent intervals, right? Just because I pushed to commit 10 seconds ago does not mean that I can predict when the next, when the push to master does not mean I can predict when the next push to master is going to be. However, we do have an aggregated form of time series data, which we regularly call metrics, a regular time series that we call metrics. And that is predictable and evenly distributed. So when we talk about regular time series and metrics, we're thinking about things like the CPU average on a machine. Like every 10 seconds, I can request the kernel, what is the CPU load average, and it will tell me. I can ask how many files are opened on a machine, and it can tell me. I can ask how many tabs I have opened on Chrome or Firefox, and I will always get a value back. What I can't do is tell you when the next tab will open. So hopefully we understand that events are raw and unpredictable, and metrics are aggregated and predictable. Examples of regular metrics is CPU usage, which we covered, the memory usage. If I want to ping google.com every 30 seconds to see what the latency is like, it's always going to be available, assuming google.com is available, and the number of processes on a machine. With regards to irregular and events, things like user data on your front-end application. You cannot predict when a user is going to click login. You cannot predict when a user is going to get their password incorrect. You probably cannot predict when a network engineer or an operations or sysadmin is in your data center and trips over a cable. Right? It's still an event that happened in the real and physical world, just cannot predict it. Right, so random screen here of a football game. I always try to just make sure people are, I think it can be difficult at first to understand this whole concept of time series and regular and events and aggregates and stuff like that. So let's try and apply it to something that we're all familiar with, even if I don't particularly like the sport myself, would be football. So there are aggregated or regular metrics available to us now. First and foremost, we have the score, which is 2-0. We also have an aggregate score over multiple games, where it's 2-3. We have the number of players on the pitch, which I would assume is 22 right now. And we have the number of people in the stadium, which will have some arbitrary value as well. That is all regular metrics, stuff that I can answer whenever I want to know. The irregular / event side of this would be when someone enters and leaves the stadium, when someone gets a yellow card or a red card, when someone scores a goal, right? The things we cannot predict. But we can tell the score based on the raw event data. So if we calculate if we look up all the events of when someone scored, I can tell you the aggregate, the metric, or the score for the game. And that's the kind of, that's the best way I think to understand the metric side and the regular side versus the events and the irregular side. Okay, and it's really important again that we understand that all metrics, every single metric in the world is an aggregation of irregular or event-based time series, without any questions. And if you have an example where you think this is not an aggregate, let me know. I'd love to hear it. And the one that people always use is the CPU average. Oh, what is that an aggregate of? Well, the CPU average on a machine is actually the aggregate of the number of instructions sent to the kernel. So, it might be a lot of data. Definitely, do I want to understand the CPU load average at one point in time, which is one value? Or do I want the raw version of it, which is 5 billion values over a 5-minute period, right? Now we can hopefully start to understand the cost that we'll cover on later. Anyway, I'm ranting. So how do we collect time series data? I'm going to talk about two different approaches. One is a product called Telegraph, which is completely open source by my former company, Influx Data. And another is Exporters, which comes from the Prometheus ecosystem. Now, what's really important here is that there are inputs and outputs in Telegraph, exporters for Prometheus, but they all do the same thing. They're all capable of scraping any piece of software that you have in your stack today and getting metrics and information into a TSDB. Right? This is not something that you have to write yourself. Someone else has already done all the hard work. Now, it doesn't matter if you're using Elasticsearch. It doesn't matter if you're using Puppet or you want to monitor your TLS expiry dates. And it doesn't matter where you want to write that data either. Like Telegraph can write to Kafka, to Datadog, Elasticsearch, and so forth. So all of this information is available. We just have to begin consuming it. And once we consume it, we can use that to understand our systems more. Better, more. Whenever I talk to anyone about the Telegraph and Prometheus side, if they do have some knowledge or in the monitoring space, there's this old argument where people talk about push versus pull. Should I be pushing my telemetry data to a TSDB, or should I be pulling it? And it's a really difficult question, and unfortunately the answer is you need both. Now, when we think about the two different types of time series data that we have, the regular stuff, the metrics, we can pull that because it's regular. Right? I can say every 10 seconds, go and fetch this value, and I will always get a value. You cannot pull events or irregular. You do not know when they're going to happen. So you have to push that data. So depending on the knowledge or how much understanding you need about a system will drive the decision to whether you need to push or pull your telemetry data. And realistically, you're going to need a combination of both. So for metrics, feel free to pull it in a regular interval. Events have to be pushed in real time, as close to real time as possible, if you need that level of understanding. Okay, now, what are the main use cases for time series data? I'm just going to cover a couple here. Number one is monitoring. When it comes to the applications that we write, when we put them into production, we need to know that they're working correctly. We also have to understand to some degree the infrastructure that our applications run on. And we may have third-party services that we interact with, maybe Auth0 if you're doing authentication that way. And maybe you want to understand that their services are healthy too, because when you have an outage, you have to really understand every aspect or every touch point to your application. Another use case for time series data is IoT and sensification. Digital thermostats, if you've got electric car engines or the GPS, even the phone or Apple Watch that you have in your pocket or your wrist or the Fitbit are always emitting metrics and events that can be consumed and aggregated to tell you how many steps you took that day, how many steps you took that week, how many times you stood up, how many times you sat down, when's the last time you had some water. All of this is really made possible by the sensification of the physical world. And the more information we consume, the more we can drive knowledge and understand ourselves as well. And then there's real-time analytics, website tracking, Google Analytics, stock prices, currency exchange rates, and if you're into cryptocurrencies. So all valid and very popular use cases for using time series data. Now, we know what time series data is. I briefly covered how we collect it. But what about the storage side? So time series databases are very, not special, but unique. They're not like general purpose databases. They are optimized for a very different use case than your general purpose database. And generally, time series databases are optimized for a very fast and consistent write path, meaning that we want to write the data much more than we ever read it. Excuse me. So time series databases have to be built for high frequency writes. And when we do read data, the read patterns that we apply to TSDBs are very different to what we would with a normal general purpose database. We're not going to do a select star from table. What we're actually going to do is show me all the values on aggregate for a certain range of time. Right? I don't need to know all the temperatures of all time and all localities. The chances are my questions are going to be suited to what was the temperature yesterday and yesterday and 3 Wednesdays ago for the last month, because I want to work out what Wednesdays are like in Scotland. TSDBs also have a concept of TTL and lifecycle management built in, which we'll talk about when we understand the cost and value of time series data as we progress through this talk. And finally, time series databases are time sensitive. You do really need to be able to expire data and write very quickly, and that will come through as we talk about it as well. What I want to quickly show you here is that the fastest growing category of database over the last, well, this is a slightly older graph now, but over the last 3 years has been time series databases. And I'm going to try and do my best to explain why I feel that is. We're in a very dynamic time within the kind of software industry or cloud native industry. As we adopt containers and microservices and cloud infrastructure, ephemeral compute, all of these things, our applications are becoming a lot simpler from a code point of view or a service point of view, but the sum of all the parts is drastically different. Understanding A microservice or cloud-based deployment software system is very difficult. And time series databases are what driving that knowledge and understanding of these systems. And that's why that line is going higher and faster than any other type of database right now. Okay, so there was a study done by thenewstack.com where they asked a bunch of developers, I'm not sure the sample size, but they said, do you have time series data and are you storing it in a time series database? And only 12% of the people said they were. So, a lot of developers acknowledge that they have time series data, but they're storing it in MariaDB, MySQL, Postgres, etc. And other than just really loving Rick and Morty and this image in particular, I don't think that, there's no real reason for this image other than that I don't think that question was probably phrased in a way that allowed people to answer it correctly, but still honestly. So I believe people did answer it honestly, but they probably weren't correct. And the reason is I don't think a lot of developers would know if they were using a TSDB or not. And I think that's because of some clever marketing of some companies I'm about to name. So if your company has an awful lot of money, the chances are you're probably using New Relic. Now, I'm sure the more than 12% of that sample size who are using New Relic, and it is a time series database. It's just not advertised as a TSDB, even though it very much is. The same as for Datadog, right? Loads and loads of companies are using Datadog for their time series data, and it is a time series database. And finally, Google Analytics is a time series database. And again, almost all developers are using Google Analytics in one way or another. So I think if the question was phrased in a way that revealed that time series data aren't just InfluxDB and Prometheus, then that number would maybe have been a little bit higher. But I don't dare to speculate how high. Okay. If we were all in the same room having pizza and beer right now, my next question would be, how many people are running Kubernetes and how many are using the time series data to monitor Kubernetes? But that's not important because I asked on Twitter the same question a little over a year ago now. And we had 902 responses, and 74% of the people running Kubernetes in production use Prometheus. That makes sense to me. They're both CNCF projects. So obviously those are going to be used together most of the time. 10% of the people that responded were using SaaS, such as New Relic or Datadog. And the one that really concerned me was the 13%. Now, I'm not sure what everyone's knowledge of Kubernetes is, but to run it in production with no monitoring whatsoever, well, that gives me the fear. So, what I would say to anyone who's watching this talk that is in the 13%, it's not too late, and we're going to change that. Okay, so as I said at the start, we are going to use InfluxDB as an example. I will keep this relatively agnostic, and these are hopefully applicable to any TSDB. Introductions, Influx is open source. Now, everything Influx Data does is open source, and Influx would say that InfluxDB is a full stack monitoring platform, and that Telegraph, which we discussed earlier, is a collector for time series data. InfluxDB is a database for storing it. They have Chronograph, which is a UI, which allows you to do dashboarding. And Capacitor is a really cool component that allows you to do real-time stream and analysis, anomaly detection of your time series data. And Influx Data are currently working on V2 of their product, which is set to be hopefully released this year. When we talk about storing time series data, or even just understanding time series data, we generally talk about points. And the best way to think about that is to phrase it as a question. At this point in time, the value of this was this. Like at, in 1944, the temperature in Glasgow was 20 degrees. Right? That is time series data. We have a time value. We have some sort of key, which was the temperature. We have a series, which is where I am, and then the value. So let's try and break that down. All points must have a series key, which we'll cover. The bits in blue are the fields. So in InfluxDB, any point in time can have multiple values. And then there's the timestamp itself. Now, the series key is where people usually get tripped up trying to understand what that is. So the series key is actually comprised of a measurement name, which we have in yellow. So the CPU load average is the measurement name. The stock price is a measurement name. And then the number of users I have on a service at any given time would be, the measurement name too. Then we have the tag keys. Now, it's a way to be able to differentiate different variations of the same measurement. So to use the temperature as an example, I could have a tag key location Glasgow, or I could have a longitude and latitude. For a CPU load average, I may want to identify which machine that load average was recorded. So I'd have host equals VM1. And for a stock price, I may have the market and the ticker to identify the price and which company on which market that price was reflective of. And here's just two more examples where I use the stock price one. You can see the market is the same, but the series is still different because the ticker values are different. Right? So the series key is a unique constraint across all the keys and values. If you're using Influx Db and you want to understand when to use a tag versus a field being any arbitrary value, then it's not indexed, which means the lookups are a little bit slower, but you can have multiple data types. Whereas tags are indexed, so the lookups and filtering is much faster, but you can only use string types. Now, what about the value of time series data? So in order to understand the value, we have to just clear one term first. I'm going to mention resolution. And the resolution just means how frequently I collect this value. So high resolution is actually a lower value. So an example of that would be if I want to collect a CPU load average on a machine at 5-second resolution, it means I collect that value every 5 seconds. A higher resolution is 1 second because I'm collecting it more frequently. Well, hopefully that makes sense. Now, the value of time series data is actually directly correlated with the resolution of the data is available. And that just means the higher the resolution, the more frequently that I collect the data, the higher value it is. I'm going to drive deeper understanding because I don't have larger gaps between the frequency of the data. If you collect the temperature of Glasgow every 6 hours, that's not that valuable. If I collect it every 1 hour, it's more valuable. I can understand the patterns over the days of the temperature. But of course, there's a cost, right? We have to store this data somehow. And the best way to do this is by not looking at the numbers. So as we run through these numbers, I want everyone just to kind of, in their head, have their favorite database of choice and try to understand at which point you got uncomfortable storing the data in your database, your favorite database, okay? I'm going to stick with an example that we've used already, CPU load average, and I'm going to try and describe this as we go. So we have a resolution of 1 second, which means I am going to collect this value every 1 second. I have one series, which just means I have one tag set, which is one machine. And I have one measurement, which means I'm only going to record the CPU load average, and that is all. To do that would be 86,400 points per day. Now, if we add on two machines, two series, right, two potential values for VM equals or machine equals, we're now at 172,800 points per day. Right? So remember, think about this in your database of choice. Am I comfortable storing nearly 200,000 points per day in a table? Okay, well, let's say our monitoring is getting a little bit more sophisticated now, and we're going to try and resemble something that more like a production infrastructure. So our resolution is still 1 second, only now we have 10 machines, which I would say is a relatively modest size production infrastructure. And we have 5 measurements. That means we're not only collecting the CPU load average, we're also going to collect how much RAM is being used, network I/O, disk I/O, and something else. So we're trying to build a fuller picture of what's actually happening on a machine. And when we do that, we're increasing the points per day. We're now at 4.3 million points per day. Right? Again, think about your database of choice here. Are you happy to write 4 million points every day to your database? And if we try and flip this over to a real-world situation, right? A real-world financial institution, right? They may want to track high-resolution data of the stock market. There are 3,300 companies on the NASDAQ. And although they would have more than one measurement, I'm only going to use one as an example right now. The reason being, I couldn't fit the bigger number on the slide. So one millisecond resolution for financial data is actually quite low. You'd probably be down to nanosecond resolution, depending on high frequency trading and what they're doing. But that's a very big number of points per day. right? I don't think I've met anyone who's answered the question of, oh yeah, I would store that in my database of choice every day, right? It doesn't really happen. Okay, but what if we changed the resolution? Remember, the value, the cost of the time series data is directly correlated to that resolution. So if I say I don't want 1 second resolution, I want 1 minute resolution, that number is looking a whole lot better again. It's still very high for a general purpose database, but much better than that last number. Right? I'm not even sure what that number is. So. But let's lower the resolution again. Right? Forget the minute. Let's just do an hour. Well, now we're back into very comfortable numbers. 79,200 points per day. Yep, I'm pretty happy with that, regardless of my choice of database. And if I do 6-hour resolution, you can see where this is going. The resolution changes everything. So we're now down to 13,000 points per day. So here's my wonderful hand-drawn graph, hand-drawn on a computer. But this graph is trying to kind of get across one point, right? Is that the green, which should probably actually just be a linear line from top left to bottom right, but if you were to store your data, you store your time series data indefinitely, the value over time gets worse and worse and worse. Right? Let's use the temperature in Glasgow again. If I store that every minute, I store the value in degrees Celsius. That's really useful information for a day, maybe for a week. And then eventually I'm like, why do I need that resolution? Why do I need to know how it changes every minute? What actually happens is over time, it's just not that useful. So what we really, really want to do is to abandon this linear decrease in value and have something that we have in the purple line where it's really, really valuable and then drops a little bit and then they're still really valuable and then drops a little bit. And this is something that is built into, I think, almost all time series databases, and it's the ability to downsample or aggregate time series data to try and ensure that we lower the resolution but still maintain peak value for what we need that data for. Okay, so downsampling, I'm going to give you an example in Influx Db. It is like 5 lines of what they call Influx QL. And it happens as a concept called a continuous query. And that just means it's a query that runs on a timer, fetches the values at high resolution, calculates the sum aggregate, here we're using the mean, and then stores that in a different, let's just call it a table to keep it simple, stores it in a different table where the value there will live for longer. And you can cascade this all the way down. So you can store temperatures at a minute resolution for 2 days, drop it to hourly resolution for 2 weeks, and then drop it to maybe 6-hour or daily resolution or daily aggregates for anything longer than that. And it's a very common pattern that you need when you adopt time series data, because we don't want to store billions and billions of rows of data that we aren't going to query in a particular fashion. But of course, we need to understand that query workload to be able to put together these continuous queries. Okay, now if anyone is thinking about events, you cannot downsample events. You can only downsample things that are predictably available because you cannot calculate an aggregate of things that we cannot predict. What I mean by that is it's very easy if I have a value every 1 hour to calculate a mean over 6 hours. If I have events that happen randomly, there's no such thing as an aggregate other than maybe the occurrence of events that happened. But that's a completely different value. So generally what people want to do is anomaly detection. And there are loads and loads of articles on Google. You can just search for Influx Db anomaly detection, or time series anomaly detection, or Python anomaly detection, which is what most of the tools are written in. And you will find loads of really cool edge cases where you can take an unprecedented number of raw events and filter them down to the outliers and get rid of all the old data. So really cool technique. Okay, so how do we take this time series data and advance our monitoring so that we can do cooler things with it? Now, to do and understand this, I want to talk about application architecture. This goes back to the DB engines graph, where I was trying to explain why time series is getting so popular. And it's because, as developers, we've kind of shot ourselves in the foot. So, when I first started writing software, my architecture was really simple. I had this application that spoke to this database, and that was it. Now, if I want to fix things when they go broken, I had very clear signals of how to do that. If the CPU usage on the machine gets too high, I could reboot it. If the memory usage gets too high, reboot it. Response times, reboot it. If Black Friday's come in and I'm a commerce store, I go out and buy mods on new servers and scale up, right? This was very simple. This was the easiest time ever to be writing software. However, excuse me, it's really important not just to have all of these signals that tell us whether our application is healthy, but we have to make the decision, when do I wake someone up, right? If you're very lucky or unlucky, depending on how you look at it, being woken up by a pager, okay, you don't want that to happen too soon, but you definitely don't want it to happen too late. And that was really easy in this kind of architecture, right? When the machine is non-responding, you can just use a health check and have that page when it fails. So health check fails, page somebody. Health check fails, page somebody. In a horizontally scalable situation, that isn't the case. Like if a health check fails on one machine, does that count as a page? Probably not. If it happens on 2 machines, maybe 1 machine's enough to keep my system operational. How do I make the decision here of when I'm going to wake someone up at 3 a.m.? And it's only by using time series data we can make that decision. So what we would do, would be to calculate or monitor all of the 500 events that were delivered to users. And if we had so many events within a certain threshold, then we would wake someone up because we believed that whatever percentage of customers getting an error was higher than we were happy to accept. Excuse me. Okay. Let's jump forward to the modern day. This is the mess we're in now. So our applications are particularly complex. The chances are you're probably working in a microservice environment, migrating to one, or someone is at least talking about it inside your organization. The goal is nice. You have smaller teams working on smaller services with a lower footprint and less chance of bugs, easier to test. The benefits of this architecture are fantastic. Unfortunately, the complexity is all being pushed to the infrastructure layer. We're now doing horizontal scaling of visual services. Some services may have canary deployments where we want to test new versions of the software before we fully release it, which means we have to do traffic shaping. We have to send a certain small portion of traffic to this service and this one. We then have a database per service, right? It's very rare people do microservices and write to a single Goliath monolith database, because then they still have a single point of failure for the system. So it's very common to have an individual database for every service, and databases are notoriously hard to operate at scale. Not only that, we have virtualized networks, right? And especially in the Kubernetes landscape with the CNI implementation. We have to be able to virtualize the network across all of the stack to do this traffic shaping and observability. And then the service meshes, right? This new trendy topic that everyone has been talking about for the last year and a half. How, in this global system of microservices, do we predict, or how do we determine when to page somebody? If one service failing, do we wake someone up? How important is that service? There's so many different questions that have to be answered. So, this is not a talk about why you should adopt cloud native architectures, but just to understand that there's a lot of convenience versus costs that have to be understood. The way that we monitor monolithic systems versus cloud native systems is very different. With monolithic systems, you can treat symptoms for a while. Right? The examples we had, CPU, memory, response times. But in a cloud native architecture, that's not going to cut it anymore. So we have to upgrade our monitoring. And that means understanding causality. Right? We have to identify the root cause where one exists and understand how to fix the system properly without just patching, scaling, or rebooting machines. That will not get us where we need to be anymore. And because we have time series data, this is the application of time to statistical mathematics. We have all of those statistical mathematics functions available to us. We can understand integrals, linear predictions, derivatives, median absolute deviation, moving averages, and Holt winters. I'm not going to cover all of these things. They are all available in pretty much every TSDB, and they allow you to do some really cool things. Rather than getting really mathematical or statistical, I want to just cover a few examples of how they would have helped me during my time as an SRE. So, as an SRE, I used to get woken up at 4 a.m. regularly. Hopefully that's no indication of how bad an SRE I was. But I guess being woken up at 4 a.m. with a disk alert being over 85%. Right? I'm not a very good morning person anymore. So when I get a page at 4 a.m. and it says, oh, there's a disk at 85%, what would I do? Well, I generally got on a computer, SSH'd onto the machine, and deleted as much crap off of that machine as I could. I would delete everything in bar log, everything in bar cache, everything in /temp. I'm just trying to buy myself time. I'm treating symptoms. Disk is full, right? Free up more space. Doesn't identify the root cause. There is definitely a better way to handle this. But again, it's 4 a.m., right? What would you be doing at 4 a.m.? If we had time series data, well, what if we could monitor the growth of the disk, use linear prediction, which says, okay, analyze the growth of this disk over the last 6 hours and predict where it's going to be in 12 hours' time. Finally, you can actually predict, is that disk going to cause an alert during the night? And if it does, you can page someone at 2 p.m. during the working hours, say, hey, if you don't clear up some space on this machine, you're going to get woken up at 4 a.m. So very, very cool application of time series data for a very trivial and common scenario. Okay, so another thing that I've had to deal with, my cable fell out. Hopefully no one was talking to me. Another thing that I've had to deal with is P99s, right? This is the idea that our application is healthy if 99% of our traffic is receiving response in the 300 milliseconds that we're comfortable with. But how do we understand that 1%? Depending on the size of your traffic to your site, that 1% is still potentially a sizable number of people that could be having problems. But maybe not enough to wake someone up, but you still want to investigate that. So by using time series data in our statistical methods, we can analyze the 1% of those requests that are anomalies, and we can use something called histogram to break that down into buckets. We can use the tag values on the series to understand if there's any commonality across the people that are experiencing problems. Now, the wider and richer the context you can add to that time series data, the more value you're going to get from using histograms in this fashion. But you can imagine that if you've got 1% of your audience, which is maybe 100,000 people, have response times of more than 5 seconds, right? If we break that down using histograms, we could maybe identify that 90% of the 1% all have IP addresses or registered users in Australia. And we could understand that they're getting a poor experience because our infrastructure is all in San Francisco or maybe in London. And we just know, oh, well, we could use a CDN edge location to improve that, improve our experience for our audience in Australia. Another really good application of time series data that for a very common scenario. And what I would suggest is when you are using histograms is that a lot of time series databases will have a format like this. This is Prometheus. Because Prometheus doesn't store event data, it only stores regular metrics. This is a pre-aggregated metric, which means you have to hard code in your code what these buckets are. So response in 300 milliseconds, 500 milliseconds, 1 second or higher. It means if you want to change those buckets, you have to then make a change to code and you invalidate all your old data. So just be careful of that. That is a compromise that you have to make for time and space, but one that is valid depending on your circumstances. And then proactive operations, if you work in commerce particularly, it can be very difficult, maybe not common anymore with cloud computing, but understanding what capacity should I scale up my servers to handle things like Black Friday, Christmas, etc. And there's a really good statistical statistical application that looks like machine learning, and then it can do predictions based on previous values called Holt Winters, which is triple exponential smoothing, where you give it loads of data and try and point out the cycles, like this is Christmas and this is Black Friday, and it can actually try and understand your growth year on year to allow you to predict how much compute you're going to need for the next cycle of that data. Very, very cool use of statistical mathematics. And what I'm just trying to encourage people to do with this time series data is to try and build as much automation into your system as possible so that you don't get woken up, you're not working on toil too much, and using causality, historical data protection, and even a little bit of machine learning if you have it available to you. But in summary, I hope you understand why you should be using a CSDB and that you probably already have time series data. So it's now time to make that more explicit and begin to store it and work with it in an appropriate fashion. Try and understand and remember the costs, right? The resolution is so important, and just knowing when to downsample that and how long it's valuable for you and your use case is one of the most important decisions you can make when you're storing time series data. Use your rollups to try and aggregate that as much as possible to reduce your cost. and try and investigate outlier detection for your events, and then build as much automation as possible to ensure that you don't get woken up when you don't need to be. That's it for me. Thank you very much for your time today. I hope you found this interesting. I will flick back over to the chat and see if there are any questions. So, thank you.
Thank you, David. I think we have one question, and it was asked fairly early on as well. So Barney asked, is there a maximum resolution for which time series DBs are useful? Would you ever collect a sample every millisecond?
Yes, collecting data at millisecond resolution is definitely more common than you would probably think. In fact, Influx Db will store data at nanosecond resolution. So, these are definitely options that are available to you. You just have to have a use case that would justify it. Financial trading being the #1 reason for storing things at above millisecond resolution. For software developers and production infrastructure, to be honest, you're going to get away with 10-second resolution for most scenarios, but that's completely up to you. Just downsample it as you can.
Okay, any more questions? Okay. I guess my question would be about cost. Obviously, if you're going to be storing this data every minute, every hour, every day, what kind of cost implication could that occur in terms of like storage or using some provider?
Okay, yeah. So there's a lot of value in high resolution data and storing it for longer periods of times from the regards of analysis and understanding and trying to work out what's going on in your system. I guess, fortunately, most time series databases are really, really good at compression. In fact, most of them implement something called Gorilla, which came out of Facebook, which is like they can store a timestamp and a single bit in a database. So using that compression, you can store billions of points at high resolution data. And the disk usage will be high, but not as high if obviously it was uncompressed. So, you can get away with a lot with time series data, but particularly they're also difficult to scale horizontally because, the high velocity writes. So you really want to have this work on a single machine with backups for those higher demanding situations, which means you are confined by the disk on the machine. So compression is good. You can store data, billions of points at high resolution. You just pay for it on disk. And of course, because their disks are SSDs, they do have a half-life or limited life now. So you have to weigh all of these things together, which I know is a very complex answer for what seems like a simple question.
I think we have just one more question. I don't know if Dan's going to put that up, but from Piotr, he asked, what was the coolest query you've made on your time series data? So any funky queries to get data out or interesting data?
So I don't know if it would count as cool. I don't think my time series data is particularly interesting. I'm generally, personally, always monitoring production infrastructure and applications. But something that's really cool is that time series data is non-relational and usually, relatively flat, and that you don't have multiple tables and you're not linking things together. One of the really cool new features of Influx Db actually is a language called Flux, which allows you to pull out your time series data, but also join that data with data from MySQL, MariaDB, Postgres, Snowflake, etc. So you can actually enrich your time series data with relational data at query time, and I think that is really cool. And I'm curious to see what the team at Influx do with that over the next 12 months. So I'll skip around to the actual question.
Okay, I think we've got another question from Barney. So there you go. So what do you miss out on if you use a product like Datadog, Splunk, or New Relic instead of explicitly using a time series database?
Wow, that is a good question. So Datadog and New Relic are great products. They're really good at answering questions that people have had before. So you can put all of your CPU, memory, response times into Datadog and to New Relic, and it will give you dashboards to answer questions like, what are my slowest queries? What are my slowest endpoints? What are my slowest this? And that works really well. But you do pay a very pretty penny for those hosted services, because storing that data and analyzing it is not cheap. When you want to have a deeper understanding, and when you want to answer questions that maybe people haven't had before, or you want to understand user patterns in your system that aren't generic or don't fit the model to what New Relic and Datadog offer, then that's when you would want to bring it in and use Influx Db, use Prometheus, use Timescale. There are a lot of time series databases out there, and they're all very, very good. So that's the best answer I have there.
Okay. I hope that answered Barney's question. I think we've finally got maybe one more, and that is from Toad. I'm not even going to pronounce his name. I do apologize. And that is Amazon Time Stream any good?
It's vaporware. They've not released it yet, right? I mean, they've been talking about it for 3 years. They announced it at reInvent in 2018, 2017. I haven't seen it yet. It's not fair of me to call it vaporware. I'm sure there's a really great team working on it, but I have no experience with it because it's not been released. So I hope it's good. I think for people that are on AWS, having that built in and have it augmented with CloudWatch would be amazing. But unfortunately, I don't think it's ever hit the public yet.
Okay, I think that's... I don't think we've got any more questions. No, okay. Any more questions? Just quickly. Okay, looks like that is all of our questions. So, yeah, I'd like to thank David once again for arranging this. Well, agreeing to my request on such short notice. Yeah, I really enjoyed it. I've learned a lot. Yeah, I've learned a lot since the last time I've used any kind of time series databases. And yeah, hopefully everyone has enjoyed this. I think maybe a few of us might go back into the social. I don't know if that's going to be still open, Dan. If anyone wants to talk, I don't know if David's going to stay or if you've got dinner or anything else to do. But yeah, once again, if you do have any more questions, we've got David's Twitter handle, which is raw code. I don't know if anyone can see that. Yeah, so just put any additional questions to him on Twitter. I'm sure he'll be happy to answer them.
Yeah, always happy to answer questions, and it's been great to be here again. Thank you for having me.
Thank you, and yeah, I think that's it for this evening. Once again, thank you to Dan for providing the platform for us to do this. But yeah, I think Dan's just posted the link. So yeah, if we all want to if you want to stay and have a chat, just go over to the social. So it's live.bigorangeheart.org/social, and yeah, I'd be happy to stick around and have a chat. So okay, I think that's pretty much it for me. So yeah, thank you very much, David, and thank you everyone for coming. See you all next month.
Yes.